Okay, two things today I want to go through with you real quick. Okay, one of them is something that we never really talked about, and it's kind of important. It shows up. I'm going to give you I'm just going to, just so we don't like waste time in class doing this, I'm just going to give you guys the paper handout and just do the test like, on your own, but follow the rules. What happens if you do something like this? What if I take the derivative of velocity from A to B? I think we mentioned this briefly. Like, what's that going to give you? If I were to, say it again? Yeah, the integral. Yeah, the integral. Sorry, did I say derivative? Yeah, integral from A to B. So let's say we're doing something like this. So this is a velocity. Take it as a vector, okay? So it's got, like, we'll just make it simple, velocity in a line, positive direction, negative direction, something like that. If I'm calculating the area under the function v of t from t equals a to t equals b, what do you think that area represents? Okay, the displacement. Yeah, that's it. Now, there's a couple ways you can think about this. Think about it in terms of what the area would be. If you look at dimensions here, what are the units? We'll just take units for a second. What are the units of velocity, standard units? Meters per second. Okay, so this is measured in meters per second. This is time. What's that measured in terms of? Seconds. So if I look at this area here in this space we've created, this two-dimensional space, I'm taking, I've got this dimension and this dimension, right? I'm finding, like, if it were a rectangle, it'd be easy. I would just multiply the height by the width. Now, it's a little more complicated because it's an integral, right? But still, it's the same concept when it comes to the units of the area. We're looking at these units times those units gives us the units of area, right? So I'm getting meters per second times seconds. So the area here is going to be in units of meters, right? So it's just going to be displacement. This is pretty easy to see, and we can see this maybe a little more, maybe a different way that maybe is even a little better if we do something like this. Well, what if we redefine velocity as the derivative of position with respect to t, right? Well, integration and differentiation undo each other, right? They're inverse processes. So effectively, we're doing that, right? We're just canceling the derivative and the integral, and what's that leave us with? Just leaves us with position evaluated from A to B, right? So it's just position at B minus position at A, which is the same darn thing as displacement, right? Okay, and then just in general, we have this is just lifted right out of our textbook. The integral from A to B of the rate of change of f equals the change in f from A to B, right? So the integral of the rate equals the value of the function evaluated over our limits. Okay, that's always true. All right, how are we doing back there? You guys testing? Questions? Say it again. Yeah, you do. Does it not give you one right now? Okay, yeah, you want one of those today? Okay, I can do that. Okay, just refresh and you should see it now. Yeah. Okay, so what about one like this? What if we want to do something like the population of the U.S. is growing at this rate? This is the modeled rate. Okay, starting where t is the number of years since 2015. Okay, let's find this integral and then we'll interpret what it means. Okay. So what do we got here then? This is going to be the integral of tell me how, this is my function, so any suggestions how I could write this integral out? Like what can I do with that number? Pull it out front, because that's just a constant multiplier, right? Okay, what's my standard form for that? That's an exponential function, but it's not a base e exponential. So do you remember what that one is? Be an a to the u, right? Remember that one? Okay, I'll tell you how you can always remember that one pretty easily is you use your change of base formula. We know that, remember, for logs, we know that I want to do, we know, yeah, that the base a log of b can always be written as the ratio of logs in any base I choose, log of b over log of a. So we'd probably use natural logs. That's what we're the most familiar with, right? So we could rewrite that as natural log b over natural log a, right? So then if I were to take a log of both sides of this, I'm going to end up with, like if I set this thing equal to y, right? If I had y equal to my integrand here, oh, you know what? That's not going to be so helpful, is it? That's going to give us the derivative, but then we'd have to just reverse that. That's how you'd have to kind of think about it, right? So the derivative, I guess it is helpful, but it's a kind of a long, maybe it's not worth this little trick. The derivative with respect to x of the base a log of u, I could just rewrite that as 1 over natural log a times the derivative of natural log u, right? Does that make sense? Well, now think about this. I don't want to go through the whole process here, but if I were going to write the corresponding antiderivative, do you see how this is what I would have to get then? Right? Because if I were writing, if I'm doing the antiderivative of, well, I don't know how to say that conveniently. You just got to memorize it, I think. Yeah, it's not worth going through that. It's easier just to memorize it than to go through this whole process. Okay, so then what do we get here? So we're just going to get 1 over log of that, right? That's my a. So my final answer is just going to be 2.867 divided by natural log of that number times a to the u plus c. Okay, so times plus c, but we're not going to do the plus c here because we're evaluating this from 0 to 5, right? Does that make sense? So there's our answer. So we end up with, if we plug this in, so I get this weird constant out front, 2.867 divided by natural log of 1.009 times 1.009 to the 5th minus, what's that base to the 0 power? Is anything to the 0? 1, yeah. Okay, and if we do that, what do we get? Well, we'll cheat and look. So we get about that, 14.661, okay, if we just plug all those numbers in. All right, so then how do we interpret that? So this, again, this is the rate of change of the U.S. population, where T is the number of years since 2015. So how do we interpret our answer then? That was about, what was it again? I can't even remember. What the heck was it? 14.661. There you go. So that's going to be the change in P, not P prime, right? That's going to be it'd be the equivalent of displacement, but for a population function. And this is in millions of people. So the U.S. population has grown over those 5 years by that many million people according to this model. Okay, make sense? And then we could go one step further if we wanted to, and we could, if we started off with 320 million, what's the population in 2020? Well, roughly 334.661 million then, right? We just add that, okay? No big deal. All right. Okay, so on to today. So we're going to look at a new technique. This is kind of our first advanced technique of integration. And let me label this. So this is what we call integration by parts. Okay, and what integration by parts does is it takes advantage of the product rule of derivatives, for derivatives, okay? And it just says then, if we know our product rule, derivative of u times v is u v prime plus v u prime, right? If we integrate both sides of this, okay, what's that give us then? Well, we get the integral of the derivative of the product of u times v, and integrals cancel derivatives, right? So we've got this cancellation going on here. So we just end up with uv, right? On the other side, we've got the integral of both of these two parts. Well, let's just split it up into two separate integrals. I've got the integral of u dv dx, right? I'm just going to make this, I'm going to split this into two separate integrals, discrete integrals, plus integral of v du dx. Well, we'll write those, we'll cancel the dx's, and we'll write these in so they look, they look more compact, right? So we've got then uv equals the integral of u dv plus the integral of v du, right? Let's just solve that for this guy. If we isolate that term, I just get the integral of u dv equals uv minus the integral of v du. Okay, you might be thinking, well, what good does that do us? I still end up with an integral in my answer. And sometimes it does you no good, but sometimes it does. It's good in situations where this is an easier integral than that. Okay, yes? What do you mean by that?
When you separate it, why don't you just take the integral of u du and the integral of v dv?
Well, because that's not what the product rule tells us, right? The derivative of the product of u times v is u dv dx plus v du dx. So we're kind of, we're constrained by what this derivative rule is. Remember, that's how we calculate, like when we want to come up with a corresponding antiderivative rule, what do we always do? We took the derivative and then we just integrated both sides to get our antiderivative rule. Does that make sense? So it's all based on this product rule that we've been using for a long time. Okay? And again, it probably looks like, at first it probably looks like, well, man, how is that going to be useful to me? Well, it's useful, again, it's useful if this integral is easier than the one I started with, because I get part of my, part of the integration by parts gives us an answer, right? It gives us just a product of two terms. It's not an integral anymore, right? Okay, so let's try this. So first of all, some guidelines, right? When would we use this technique? Well, we're only going to use it when it makes sense. So some things we need to know: dx is always going to be a part of, I'm assuming x is our independent variable. That's always going to be a part of dv, right? So like we're going to have like the integral, like down here, for example, we've got the integral of x e to the x dx. Well, that dx, when we start doing this process, what we're going to end up doing is choosing a u and a dv. We're going to split our integral up into those two parts, and obviously the dv part is always going to get the d whatever, dx, dt, whatever it is that we're integrating, right? Whatever our variable of integration is, that gets absorbed into the dv part of our integration by parts formula, right? dv should be easy to integrate. In other words, it's got to be no more complicated than the original integral was. If it gets increasingly complex, what's the point of doing this, right? Okay, and what else? If the new integral is more complicated, try flipping your choice around and see if the other way works. And it may not. There's some other techniques we might have to resort to if this doesn't work. Okay, so let's try this guy. So what do you think? What would be, I've got to be able to make a substitution here so that this is going to match the integral of u dv. I've really got two choices, right? I could either let the u be e to the x, or the u equal x. And the dv would just be the other part of it. Does that make sense? Okay, let's just try them both and see what happens. So what if we try letting u equal x and dv equal e to the x dx? And the way I'll have you guys write this down is you'll just make like a little table. You'll say, I've got u and I've got dv, right? So if we do this substitution, we'd have u equals x, dv equals e to the x dx. And let's fill in the blanks. Okay, well, what does that give us for v? If dv is e to the x dx, v is the antiderivative of e to the x dx, what would I get? And really all I'm doing here is I'm just saying v equals, what is that? E to the x, within a constant, but we're not going to put the plus c there because we're going to get a plus c at the end of everything anyway. We'll just subsume all of our constants into one great big constant at the end. We don't need to hang on to individual ones. So we just get e to the x. How about on the other side? If u equals x, what does du equal? dx. Just equals 1 dx, right? Okay, so that's what we get if we plug into our formula then, right? Remember what it was. The integral of u dv equals uv minus the integral of v du. So I'm getting an x e to the x outside minus the integral of e to the x dx. Well, that worked, right? The integral of v du is easier than the integral of u dv, right? That's just e to the x, isn't it? Everybody see that? And so my final answer just looks like that. X e to the x minus e to the x plus c. Okay? So now what if we had made the other choice? Well, if we'd made the other choice, it wouldn't have worked very well in this case. If we picked u equals e to the x and dv equals x dx, well, now if I take the antiderivative of x dx, I get x squared over 2. It's getting more complicated, right? So I get u times v. That part's okay, I guess. But look at my integral. I get the integral of x squared over 2 times e to the x dx. That did the opposite of what we wanted. It didn't turn the integral into something easier. It actually made it something more complicated that I don't have a standard form for, right? So that one was a bad choice. Integration by parts wouldn't work with that choice of u and dv. Okay? So we can come up with sort of some guidelines then. You know, you'll see a pattern here right away. I think I already looked at those, but right here. Okay? So some general guidelines. If you've got functions like exponential functions or trig functions or things like, you know, any kind of trig function. Could be sine, could be secant squared, anything like that. Well, then what's your choice of u going to be if these transcendental functions, that's how we label those things, if the exponential or the trig functions are being multiplied by a power function, right? Then you're always going to want to choose the power function as u, and the dv is going to be the transcendental part of that, right? Does that make sense? Okay, and if we've got, so that's always going to be the case. And how come? Well, because if I take the integral of transcendental functions, they don't really get more complicated. They just turn into other trig functions or other exponential functions, right? But the power function does get reduced in complexity if I differentiate, right? So usually that power function is going to be our choice of u, okay? How about if we've got something like this, however? What if we've got a power function times an inverse trig function? Well, inverse trig functions, the integrals are horrible, right? That's not going to do us any good. We're going to get these weird natural logs, and it's a mess. So we got to go the other way with this. We've got to say, okay, the only way this could possibly work is if we end up with the u being the inverse trig function and the dv being the power function, right? Because even though the dv might get, that when we integrate, the power function is going to get slightly more complicated in that it's going to become a slightly higher power, it's still just a power function, right? It's still something we can deal with. And then finally, if we've got something like a log function times a power function, well, then we want to let u equal, again, the log function in this case, because the log function is easy to differentiate, but it's a bear to integrate, right? So there's some general guidelines. Let's just try some of these. So what do you think for this one then? We're going to come up, this isn't a formula that you guys have to memorize, but this is a pretty standard formula in a integral table, okay, one that we use quite a bit. So after a while, like in college when you're doing solving lots of differential equations, this will just be one that you'll remember, okay, because you use it so much. What would I choose here for my choices for u and dv? What do you think u is going to equal in this case? Use the one that's easy to differentiate. We're going to calculate du. So natural log x. So then what's du? 1 over x dx, right? So we'll just call it dx over x. Okay, that leaves us with dv being what then? What's left? dx, 1 dx, right? So then what's v? What's the antiderivative of 1 dx? X. Okay, and we got it then, right? We get the integral of u dv equals uv. So that's going to be 1 over x. It's going to be this, isn't it? It's going to be, whoops, other way around. There's uv. So I just get x log x minus the integral of v du, which is x times dx over x. Well, the x's cancel, right? I just get the integral of dx. That's just x, right? So here's my answer. Okay, everybody see how that works? Questions? Okay. How about this one? What would I choose for my du this time? And it's an inverse tangent, not a tangent. Tangents would be easy to differentiate. I mean, would be, they'd be easy to integrate, right? So what am I choosing here for u? Inverse tangent, yeah. So then du is what? Just dx over 1 plus x squared, right? And dv would just be dx. And so v equals x. And we would end up getting uv, so x times inverse tangent of x minus the integral of v du. So I'm just getting the integral of x dx over 1 plus x squared. Okay, that's a little bit tougher, but we can do that one. That's that stuff we were just practicing in 6.5, right? That's the u substitution stuff.
Is it UDU minus V, or UDV minus VDU?
It's uv minus vdu, integral of vdu.
Why is it minus? Is that just
Well, because that's what we came up with when we did our, way the heck back here, where is it? Right there, right? Because of this, right? When we solve for integral of u dv, I just have to subtract that term to the other side. So what would my u substitution be now? And now we're done with integration by parts. Now we just have to finish the deal by doing the integral that we're left with, right? We have to simplify the integral of v to u, which is this. So what's my choice of u there? I've got to make a substitution where I'm going to get, with constant, I'm going to get a u du. So what do you think? What do you think?
when you integrate it, you get like a DU back.
Well, but now we're just doing regular integration by substitution. So now I just need to be able to make a change of variables is all I'm doing. I want to pick a u so that this integral is going to look easier, right? And then I'm going to calculate du based on my choice of u. Well, what's it going to be? How about 1 plus x squared? So then du is just 2x dx. And what do we have? Well, we don't have a 2x dx, but we have an x dx. So x dx would just be 1/2 du, right? And look what we get then. We've got there's our u, and here's our 1/2 du, right? So this just looks like I get the integral of my u's on the bottom. Oops. and there's my 1/2 du. Well, what's the integral of du over u? Natural log u. Yeah. So then we just get this. All right? When I reverse the substitution, okay? And I don't need I don't need absolute value bars because 1 plus x squared is always positive value, right? Okay. So that's the stuff from the 6.5 assignment. So you got to get some practice on that, evidently. That's just u substitution stuff. Okay, how about this one? What are we going to do here? What's our u? Say it again. X squared, yeah. And du would just be 2x dx, which means that dv is just e to the x dx. So what's v? What's the integral of e to the x dx? E to the x. You know, plus c, but again, we don't include that. Okay, so then this gives us, if we follow our pattern, integral of u dv equals uv minus the integral of v du. What's that giving us? U times v is just x squared times e to the x minus the integral of v du. Well, that I can pull the 2 out front, and that's just x e to the x dx, right? Okay, did that help? Yeah, it did. It helped because look at my integral. My integral is easier than the first one was. What am I going to have to do to solve this integral, though? I mean, I can't use substitution, can I? Just plain old u substitution. Because if I pick u equals e to the x, well then du is just e to the x dx, right? It doesn't really work here, right? See what I'm saying? I've got that x left over that if it was just e to the x dx, I'd be fine. The answer would just be e to the x. But couldn't I just do integration by parts again? But it's an easier integration by parts, right? So we would just go again with everything inside the blue box just to do that integral. We would say u equals x, so du equals dx. dv equals e to the x dx, so v equals e to the x, and look what we get. Everything in the blue box just becomes x e to the x. Oh, man. Minus the integral of e to the x dx, right? That's my blue box. Put it in brackets, which is equal to x e to the x minus e to the x plus c, right? But what am I doing? I'm subtracting 2 times that whole thing. Okay, so my actual answer then is x squared e to the x minus 2 times that whole thing. I could distribute the negative 2 if I want to, right? And I get my final answer. X squared e to the x minus 2x e to the x plus 2 e to the x plus c. Okay? Make sense? All right.